Well, welcome back everybody, and we'll take a look in this video to kind of focus on one of the topics that we talked about in the previous video where we were looking at the 4 factors that influence the outcome of our regiochemistry of our substitution versus elimination reaction. Here we want to focus in on the topic we're talking about making good leaving groups. And so what we want to do is try and cover a couple of strategies to make bad leaving groups into much better leaving groups to allow us to kind of accomplish the transformations that we want to make on our organic molecules. So here, for example, is one of the transformations we might want to make. Well, we want to take something like a primary alcohol and convert it into a primary alkyl halide. So convert the alcohol into a halide. Now we might be tempted to take something like Cl- as a nucleophile directly with the OH, but of course that's not going to work. This particular reaction as drawn would give us no reaction. And why is that? We analyze a little bit of what we're doing. Is we've got OH minus as our leaving group. That's the conjugate base of water, pK of 15. That's not a very good leaving group. We said things that make strong bases, we just typically don't observe them being good leaving groups at all. So OH minus is not a leaving group. And Cl- is not a good nucleophile. That's the conjugate base of HCl, which is a pK of -7. That's a relatively poor nucleophile. It's small and not very polarizable compared to some of the other nucleophiles we might imagine. So overall, this reaction is set to fail. Now, there's a couple of strategies we can use to accomplish this particular transformation to make OH into a good leaving group. And so one of the strategies is this one here. We use this reagent called thionyl chloride. So thionyl chloride, a very specific reagent of carrying out this particular purpose, where it will react with primary alcohols and convert them into primary alkyl halides, primary alkyl chloride specifically, turns it into the chloride. And then that chloride could be used as a better leaving group for many other sort of the steps or other kind of substitution chemistry. So we can turn that bad OH into a good leaving group. And this works because the intermediate that we generate on this pathway that's the intermediate that we generate on this pathway, and so that turns that into a good leaving group, activates that oxygen as a good leaving group and gets displaced with the chloride ion that's also present there. So we're not breaking the rules of organic chemistry, we're just using a different method to achieve this particular transformation. So that's one of the methods that we have for turning alcohols, those bad leaving group alcohols, into good leaving groups. So let's see if we want to try another kind of transformation. So maybe something like this. If we've got a secondary alcohol, can we convert that secondary alcohol into a secondary functional group, in this case a nitrile or cyano group? So we're using sodium cyanide, NaCN, so that's not a very strong nucleophile. Not a very strong nucleophile. It's the conjugate base of HCN, which is pK of 9.2. And OH minus, of course, is not a leaving group. So trying to push an OH minus off with something that's not a very strong nucleophile, that's not a very likely strategy to succeed. So what can we use to overcome this? We can use something called tosylates. We can use a strategy of something called a tosylate. So let me draw this out in some detail, and then we'll take a look at how this works. So here I've drawn it out, and I'll fill in the details of this in a second here. So we've got tosyl chloride. And we use pyridine as the solvent for this particular reaction. And the pyridine, of course, is a molecule we talked about a long time ago when we were talking about aromatic molecules. Here we're using it as a solvent because it just works very well for this particular reaction. Okay, so what's this tosyl chloride? So it's called para-toluene sulfonyl chloride. There's the chemical structure of tosyl chloride. It's an aromatic ring with a methyl in the opposite or para position, and this sulfonyl chloride. And that reacts with the alcohols to make these so-called tosylate esters. So you can make that tosylate ester. So we have to do one chemical reaction on our substrate first. We make this tosylate ester. And then the next step is, now that we've made that tosylate ester, we've made something that's a very good leaving group. So we haven't done any kind of chemistry at the electrophilic carbon yet. We haven't displaced anything. We've just modified the OH group into this more active ester. And we can tell we haven't done anything to the electrophilic carbon because the stereochemistry of that electrophilic carbon is still the same. And now we can displace this with whatever nucleophile it is that we'd like to use, in order to displace this. So here we can now use sodium cyanide. And we're cleanly observing SN2 because we get full inversion. We get inversion of that stereogenic center. We get complete inversion of that stereogenic center. So the cyanide is acting as a nucleophile, and that tosylate ester now is acting as a very good leaving group. And of course, the leaving group is this. The leaving group is this, which is the conjugate anion of something called para-toluene sulfonic acid. And so TSOH, we sometimes abbreviate that, TSOH, that's got a pKa of -3. So that para-toluene sulfonic acid, this anion that we've drawn is the conjugate base of that acid, but that's a very, very strong acid. So this makes a really good leaving group, stabilized anions. And even if we didn't know what the pKa was, just being able to look at that anion and being able to think about the resonance contributors we draw for that particular anion leads us to believe that would be a pretty stable anion, even if we knew nothing about the pKa of it. And of course, this is in the pKa tables that we have in our textbooks and on the data sheets. So a very effective strategy for making this into these tosylates, or these alcohols, into a very good leaving group. And we can also, there's also a couple of other potential analogs that we can use as well. Our textbook mentions these, so I think I thought I'd introduce them here. So these are called mesolates or triflates. So a methane sulfonyl chloride or sulfonic acid you would use to generate this, or a trifluoromethane sulfonyl chloride or sulfonate ester. So triflate is the abbreviation name that we use for both of those. These are both acceptable, and you can make these, of course, from the corresponding acid or corresponding chlorides. So from the corresponding chlorides, you can make both of these from the corresponding chlorides, the mesyl chloride or triflic chloride. But the overall strategy is the same. We turn a bad leaving group OH group, bad leaving group as an OH group into a bad leaving group into a good leaving group that leaves, generates a stable anion, and allows us to get a good leaving group on those kind of functional groups. And these are the ones, the main one that we encounter, these oxygens trying to turn an OH into a good leaving group. And so we'll spend quite a bit of our time looking at some other examples of this when we get to the question and answer session this week. So for now, we'll leave the video there and put that up and take a look at some of the strategies to make good leaving groups.